Coronavirus Classroom. I'm Janessa Jacobs, and this is A&P 1 Exam 1 Review. I am of the belief that it is ridiculous to have exam reviews from your living room, so I'm always ridiculous in exam reviews, so be ready for that. But what are things that you can do to review? You can come into each of your exam modules, and there's an exam 1 review right here. So I'm going to go through this a little bit right now with you. So chapter 1, show your understanding of anatomy and physiology, the topics studied by each, levels of organization in the body, anatomy specific terminology, including directional terms, all that jazz, homeostasis, feedback loops. Chapter 3, general structure of a cell, including the plasma membrane, transport processes, including passive and active mechanisms. Number 4, all of our tissues. Chapter 11 is nervous tissue. So I actually kind of want to start our review right here at tissues and then like break it out into looking at nervous tissue, and then we'll come back through these other ones. So just be aware you've got that at your disposal anytime you want to study for your exam. Okay, so if we start as tissues, these are groups of cells that are performing a similar function and working together ultimately to form organs. So we'll get there. We said that we had 4 main types of tissue. Muscle tissue, and we said we had skeletal, that moves the bones, cardiac, that we find in the walls of the heart and moves blood through the heart, and smooth, that we find in the walls of our hollow organs. So skeletal muscle tissue we will talk about in chapter 9. Cardiac muscle tissue we will talk about in chapter 18, I believe, next semester. Smooth muscle we'll talk about kind of all over the place. All right, so we're not really going to talk about that now. The other type of tissue that we have is nervous tissue. We are going to talk about this now because chapter 11 is on this first exam. So let's come back to this in a minute. The other 2 tissue types that we have are connective tissues and epithelial tissues. And we said that epithelial tissues are going to be the tissues that line things, cover things, form boundaries between different environments. So let's start there. Epithelial tissues, we classify them based on the number of layers and the shape of the cell at the apical surface. So simple tissues have 1 layer. Stratified tissues have more than 1 layer. Our first type is simple squamous epithelial tissue. This is the thinnest possible barrier that we find in the body. We find it in places like the lungs, where we need to allow for the rapid diffusion of oxygen and CO2. We find this lining the heart, lining your blood vessels. It lines your lymphatic vessels. It forms your serosa, one part of your serosa, so our serous membranes. It helps to form part of the glomerulus or the renal corpuscle in the kidneys, so it forms the glomerular capsule. Okay, thinnest possible barrier. Okay, so then next, what if we have 1 layer of cuboidal cells? That would be simple cuboidal. It functions to do absorption and secretion. Where do we find it? We find it in the kidney tubules. And we find it forming the secretory and duct portions of smaller glands. So secretory and duct portions of small glands. Okay, simple columnar. 1 layer of columnar cells. Now here we can have a ciliated and a non-ciliated variety. So for simple columnar, the ciliated variety we find in portions of your respiratory tract, like in your small bronchioles. We can find this in some of our secretory portions of larger glands, and I think the duct portions, but this is for larger glands. We find the non-ciliated variety. I think probably the secretory portions of glands also the non-ciliated. ciliated in the respiratory tract. The non-ciliated would be in our secretory portions of glands. The non-ciliated variety we can also find throughout the GI tract. So lining the lumen of your alimentary canal, most of your alimentary canal is a simple columnar epithelial tissue. So the function, secretion and absorption, secretes digestive juices, absorbs nutrients. The ciliated version in your bronchioles help to beat mucus, so it secretes mucus and beats that mucus up the mucus escalator. Simple columnar function, secretion and absorption, secretes in the kidneys. Secretion and absorption is all weird, but we'll get there. Secretes stuff for our glands. Simple squamous function allows for rapid diffusion of materials. We find it in areas where we need that, like the lungs for the rapid diffusion of gases, the blood vessels where we need the rapid diffusion of gases and nutrients. Okay, so those are our simple epithelial tissues. And really, we only have a couple stratified tissues that we need to worry about, because stratified cuboidal and stratified columnar are very rare. So we're just going to kind of get over that. We didn't talk about pseudostratified ciliated columnar. So there is one more type of simple epithelial tissue. That's the pseudostratified columnar. And it's pseudostratified because it is really only one layer, but it looks like it's multiple layers because not every cell reaches the apical surface. So it looks something like that. The ciliated version is going to be found in most of the upper respiratory tract, where it functions to secrete mucus and repel that mucus. The non-ciliated version we can again find in the secretory portions of larger ducts and some of the sperm-carrying ducts in the male. So, okay, that's our pseudostratified columnar epithelium. The tissue that you look at in lab is like the trachea, where you can actually see cartilage in there too, and then we'd see the ciliated version, where we've got cilia on the top to help repel that mucus in the respiratory tract. Okay, those are simple. As far as stratified epithelial tissues go, we've got stratified squamous, and we've got two versions, a keratinized and a non-keratinized. So your skin is what we call a dry membrane, your cutaneous membrane, and this is the keratinized stratified squamous epithelial tissue. And what keratin is it's this like water-resistant protein that makes your skin a dry membrane, so that we don't take on too much water, we don't lose too much water. Keratin gives it water resistance. Okay, this is what we find in the epidermis of our skin. The dermis of our skin is connective tissue, two types of connective tissue. But the epidermis of our skin is the keratinized stratified squamous epithelial tissue. We'll talk more about that when we get to the integument. The non-keratinized version is wet, so it functions to secrete mucus. All of our stratified squamous epithelial tissues resist abrasion, so we can slough off dead cells on the exterior surface. The non-keratinized version we find in places that need to be wet but are also exposed to abrasion. So lining the oral cavity, lining the oropharynx, lining the esophagus. There's a little bit at the superior aspect of the larynx. And then we find it in the anus, a little bit of the rectum, and the vagina. So non-keratinized is going to be wet, but abrasion resistant. So we find this in the oral cavity, esophagus, vagina, anus are the biggest locations. The keratinized version is the epidermis of your skin. Okay, the last type of epithelial tissue we have is also a stratified tissue. It's called transitional epithelial tissue. And it gets this name because the cells transition. When the bladder is empty, they look more cuboidal. And as you start drinking more fluid, they start stretching out and looking more squamous. They transition in shape. And how you're going to be able to tell it apart from like a non-keratinized stratified squamous epithelial tissue, even when the bladder is full. The apical cells stretch out, sure, but pretty closely underneath there, the cells are going to look cuboidal, or they're going to look more round, whereas in our non-keratinized stratified squamous epithelial tissue, the apical layers, several of the apical layers look more squamous. So that's one thing to be aware of. Okay, those are our epithelial tissues. How about connective tissues? Well, we said we could clump our connective tissues into connective tissue propers There are 6 of those, 3 that are loose and 3 that are dense. And this is really what we're going to talk about for this first exam. I mean, you still need to be aware. If I were to give you a multiple choice question that said the following are connective tissues, and I were to left bone in there, and you weren't to choose that answer that had bone in there, you'd be wrong because bone is a connective tissue. So the other connective tissues that we have aren't connective tissue proper, they're a little weird. We have cartilage, bone, and blood. So blood we're going to talk about in chapter 17 next semester. Bone we're going to talk about in chapter 6, I want to say. Cartilage we'll also talk about in chapter 6. I mean, we'll talk a little bit about it now. You should know the 3 general types of cartilage and where we find them, but we'll go into greater detail when we get to the skeletal system. Okay, so for this test, connective tissue proper. Connective tissue proper, loose. We've got 3 types. They have a loose arrangement of their cells and in their extracellular matrix. The first is areolar. This is the most abundant. It forms the lamina propria that we can find underlying like our mucous membranes and our serous membranes. It forms most of the underlying epithelial tissue, or the underlying tissue that served our epithelial tissue, because if you recall, epithelial tissue do not have their own blood supply. Areolar tissue brings those tissues blood. It's pretty great. So that's the most abundant and most important. It really connects one tissue type to another. Adipose tissue is the next type. Recall here we have fibroblasts that are pretty sparse, and they're secreting an extracellular matrix that's similar to areolar in that it's got all 3 fiber types. It's kind of this viscous, pretty thick ground substance. But it's in adipose tissue, there's really low levels of that ground substance. And instead what we see is a high number of adipocytes, those cells that secrete those cells that accumulate a large fat droplet that acts as a reserve fuel store. It also helps to protect some organs, things like that. What's our last type of loose connective tissue is, what do we got here? We've got reticular. And in reticular connective tissue, we have a high proportion of those reticular fibers in this loose arrangement, and it forms the stroma of our lymphatic organs, where we need to be able to allow whole cells in and out. So it's pretty rare, but it's also loose because we have this kind of these fibroblasts that become reticulocytes and secrete this extracellular matrix that's pretty thick, but really highly rich in reticular fibers that are going to form the stroma for our lymphatic organs. And we've got 3 types of dense connective tissue proper, dense regular, dense irregular, and elastic. In our dense regular connective tissue, this forms our ligaments and tendons. We have this really regular arrangement of a high proportion of collagen fibers packed very densely together. There's a low level of extracellular matrix secreted by the fibroblasts. Very low levels of ground substance, high proportion of collagen fibers squashed together like that. Dense irregular connective tissue has kind of still densely packed together, but now our collagen fibers are kind of in this irregular fashion. There's not as much space, not as much ground substance, so that what this does, these 2 tissues resist stretch. Dense regular resists stretch in one direction, dense irregular resists stretch in many directions. And we'll find dense irregular forming the bulk of our skin. So the deepest layer of the dermis, called the reticular layer of the dermis, is dense irregular connective tissue. Sitting right on top of that is the papillary layer of the dermis, is areolar connective tissue, which is supporting the keratinized, stratified squamous epithelial tissue. All those 3 tissues form your integument. We'll get there. It's got its own chapter. It's its whole own system. Elastic connective tissue has a high proportion of elastic fibers, and here again they're going to be really squashed together. You can tell the elastic fibers squashed together apart from the collagen fibers squashed together because collagen fibers are thick pink bands. Elastic fibers are little black ones. So you see a high proportion of elastic connective tissue in the great vessels leaving the heart, and that will be what you're looking at in the slide. So it'll be really, you'll see like red, but you'll see lots of little black lines in there. It's a high proportion of elastic fibers. Again, low levels of kind of sparse but viscous ground substance with high levels of elastic fibers, making that the rest of the extracellular matrix, giving us a dense arrangement of that connective tissue proper. Cartilage we find in the skeleton. Hyaline cartilage forms the fetal skeleton, forms your nasal cartilages, forms your costal cartilages, covers the ends of long bones and joints. The most abundant cartilage. Then we have elastic cartilage, which is different than elastic connective tissue. Elastic cartilage forms your external ear and the epiglottis that covers your larynx when you're swallowing so that food goes back down your esophagus and not into your respiratory tract. And then fibrocartilage we find is like the pubic symphysis here, or these intervertebral discs. Fibrocartilage resists compression. Bone, we've got spongy bone and compact bone. We're going to talk a lot about this semester. Next semester we'll talk about blood and go into the nitty-gritty of that. That is your review of, pretty much your review of chapter 4. I mean, we talked a little bit about this already, and we said there was nervous tissue. Let's review what you need to know about nervous tissue from chapter 11. All right, there's a lot in chapter 11. Functions of the nervous system, divisions of the nervous system, like all that jazz. So our central nervous system has our brain and spinal cord, which is talking to our peripheral nervous system that has our nerves and our ganglia, sensory receptors talking to those nerves. So we've got a division that's bringing stuff in. The sensory division, or the afferent division, is going to bring stuff from receptors along nerves and then into our central nervous system, which is going to decide what to do about it. So we've got stuff that we're aware of, that's somatic, and we've got stuff we're not aware of, that's visceral. So that's still sensory information coming in through nerves and going into the central nervous system, which is the brain or spinal cord. Okay, you can also put output. So our central nervous system, brain and spinal cord, are going to send commands through an efferent pathway through nerves that have neurons that are going to bring out our motor or our efferent commands. Okay, so the somatic division is what you have control over. The only thing you have control over is skeletal muscle. Okay, the autonomic division is what we're going to talk about at the end of the semester because it controls almost everything in your body. Everything we're going to talk about next semester: cardiac muscle, smooth muscle, and glands. Okay? So in the autonomic division, there's a fight or flight division, the sympathetic nervous system, which is in control of fight or flight, and the parasympathetic nervous division, which is in control of resting and digesting. But we'll get there, okay? So that's the breakdown of like the divisions of the nervous system. Think about the functions of the nervous system: to intake information, integrate information, and then output so that we can maintain homeostasis. That's its big job. The nervous system is going to communicate messages all around the body through neurons that are in nerves or in the central nervous system in tracts. Yeah, so be aware of that. What else? Kind of the hardest part is really when we look at the nitty-gritty of nervous tissue. So tissue is when we have or when we've got two or more cell types working together. So we've got, in the nervous system, we have glial cells, and then we've got neurons. Neurons are the hard part. It's going to be the hardest part of this test probably. Super, super important. It's why we start here, because neurons control everything else. And they're hard now and they're hard later, so we might as well get it over now, so when we talk about everything else, you know what's going on. Okay, so in our central nervous system, we've got some glial cells, and in our peripheral nervous system, we've got some glial cells. In the central nervous system, we've got astrocytes. Are the most abundant, they're the most important, they support our neurons, they help keep the chemical environment steady, they help the growth of neurons, making sure that they're going to the right place, they support synapses, they're super important. They fill the space of dead and dying neurons, really, really important. And if you don't know the functions of them yet, then make a note card, look at your book, because I've already told you them. I don't need to write it down again. I've told you the functions, I wrote it once, I just said them again. Make yourself a note card and study it. The next type of glial cell that we have in the central nervous system is what's called a microglial cell. And these are little phagocytes, provide the only local immunity in the nervous system, which is pretty crazy. If your immune system starts talking to your nervous system, it's going to be chaos. So yeah, these are local phagocytes that can gobble stuff up. The other kind that we have are called ependymal cells. These line the fluid-filled spaces, ventricles in our fluid-filled spaces. They've got cilia, so they can help to move the cerebrospinal fluid that is moving through those fluid-filled spaces. In places called the choroid plexus that are free of the blood-brain barrier, ependymal cells form cerebrospinal fluid. That's a way that we can bring chapter 3 information into this test. Blood-brain barrier is what exists because the endothelial cells, which are simple squamous epithelial cells lining the blood vessels that serve the brain, are joined by tight junctions, cell junctions that we talked about in chapter 3. So those tight junctions between our cell membranes link those blood vessels together so nothing can just passively slip through there. And then the astrocytes also help because they wrap these little feet around it and also help create the blood-brain barrier. So that's how those things can kind of come together. So be aware of that. Ependymal cells in this area called the choroid plexus are going to be able to pull whatever they need from the blood because we're free of blood-brain barrier in choroid plexus and create cerebrospinal fluid. So that's going to be important. The last type of glial cell we find in the central nervous system is the oligodendrocyte. And these are the myelinating cells in the central nervous system. So they myelinate neurons so we can have saltatory conduction, which is really fast conduction of our action potentials. In the peripheral nervous system, we have 2 Schwann cells, also called neurolemmocytes, and our satellite cells. So our satellite cells are like the astrocytes. They're kind of covering the soma of our neurons out in the PNS. So in the ganglia, you'd find our satellite cells covering the cell bodies. Satellite, I think I got that. Schwann cells, or our neurolemmocytes, are the cells that are going to be the myelinating cells in our peripheral nervous system neurons. So we would find those running in nerves. Okay, those are glial cells. Neurons, the big important functional cell of the nervous system, has 3 parts. Here's our soma. This is the cell body. It contains the nucleus, the brain of the cell. On it, we have a bunch of dendrites. Our dendrites and our soma together are going to form the receptive segment. This part of the neuron is receptive to stimulation from another neuron. And it contains ligand-gated channels. So what's going to be released from our presynaptic neurons here are neurotransmitters, which are chemicals. So they're going to cross the synaptic cleft and bind to chemical-gated receptors here, or ligand-gated channels. So in the receptive segment, the only types of channels that we have are ligand or ligand-gated channels. Those channels are neurotransmitter receptors. So if the neurotransmitter crosses the synaptic cleft and binds to its neurotransmitter receptor, and that receptor is a ligand-gated cation channel, then what's going to happen is I'm going to have potassium leaving, but sodium entering, and a net influx of sodium that will give me an excitatory postsynaptic potential. This is a graded potential, and it is a depolarizing event that moves me closer to threshold. So I get closer to threshold when I open a ligand-gated cation channel. Okay, if I have another neuron here, presynaptic neuron, and when I release neurotransmitter, that neurotransmitter crosses the synaptic cleft and binds its receptor, which is a potassium channel. So this would now be a ligand-gated potassium channel. That's the neurotransmitter receptor. Which way does potassium move when it moves through a channel? It moves out of the cell down its concentration gradient. So if I have potassium exiting, this is a positive charge leaving, this is a graded hyperpolarizing event that will move me further away from threshold. Okay, now what if I have a presynaptic neuron that is releasing a neurotransmitter that when it crosses the synaptic cleft, it binds its neurotransmitter receptor, and now that is a ligand-gated chloride ion channel. Where is chloride ion concentration higher, inside or outside the cell? It's higher outside here with sodium. So chloride ion, which is an anion, is going going to enter the cell, bringing a negative charge in. So this will be a graded hyperpolarizing event. Hyperpolarizing and depolarizing events are summed in the receptive segment to determine whether or not we're going to fire an action potential. The first part of the axon is this enlarged region here, the axon hillock, which is also sometimes called the trigger zone or the initial segment. And it's a little bit bigger, so just for that reason alone, it has more voltage-gated sodium channels, but it has more voltage-gated sodium channels. So this is going to make it sensitive to depolarizing stimuli. So as long as I hit the threshold of negative 55 millivolts here from summation of excitatory postsynaptic potentials, then I will fire an action potential. So before we get there, let's talk about summation. One excitatory postsynaptic potential is not going to move me from my resting membrane potential of negative 70 millivolts to negative 55. But if this neuron fires and then fires again, then I would have temporal summation of these excitatory postsynaptic potentials. I would reach threshold and I would fire an action potential. Now, if I had one excitatory postsynaptic potential here and another excitatory postsynaptic potential here, and they fired at the same time, those would sum up spatially, and I would reach threshold, and I would fire an action potential. Now, if I were to get to depolarizing if I were to get to hyperpolarizing events that add up in time, then I just move further away from threshold, and I inhibit this neuron from firing an action potential. If I were to get one excitatory and one inhibitory at the same time, then that would be spatial summation, and they would cancel each other out, and I would not get an action potential. So the receptive segment has that job to do. Sum up all of our excitatory postsynaptic potentials, which are occurring because we're opening a ligand-gated cation channel, allowing for a net influx of sodium. Those are all summing up either in time, where we have rapid fire transmission coming from our presynaptic to the postsynaptic neuron, or we can sum all of these up in space, where multiple presynaptic neurons are hitting this postsynaptic neuron at the same time. And again, our inhibitory postsynaptic potentials are going to be these small, graded hyperpolarizing events that move us away from threshold. They can happen when we open a potassium channel, which allows potassium out, or when we open a ligand-gated chloride ion channel, which allows chloride ion in. All right, assuming we reach threshold. When we get here to the axon, what we have in the axon are voltage-gated sodium and voltage-gated potassium channels. So these voltage-gated channels are going to conduct our action potential down the axon to the terminal without decrement. I should probably use colors that are further away from each other. So our voltage-gated channels open at a threshold, which is negative 55 millivolts. And what's going to happen at this threshold is sodium, when our voltage-gated sodium channel opens, sodium goes into the cell, rushes into the cell. It's a positive charge coming into the cell, and it's rushing in until positive 30 millivolts. And that positive 30 millivolts then is going to be the trigger that opens up our next voltage-gated sodium channel. And sodium rushes into the cell until positive 30 millivolts. That positive 30 millivolts is going to continue downward. Sure, we can feel it backwards as well, but as soon as we hit positive 30 millivolts, these channels are going to inactivate. We swing the inactivation gate shut, and now we cannot open these channels, these voltage-gated sodium channels. Then what we see is the effect of our voltage-gated potassium channels being open, and potassium is going to exit until we get to negative 90 millivolts. So it's going to hyperpolarize, which means that this part of the neuron is refractory, while this part is depolarizing. This part is receptive. So this positive 30 is going to depolarize this will inactivate, and the action potential will move in one direction away from the soma until we get to the transmissive segment. When we get to the transmissive segment, now we can have several branches called teledendria, or we can just have one. But what's going to happen now is when our depolarizing swing gets down here, it's going to open our voltage-gated calcium channels. Calcium is going to flood the cell, move these regulatory proteins that are holding our synaptic vesicles of neurotransmitters stored there. Calcium enters, moves those, neurotransmitter is released by exocytosis, and now this becomes the presynaptic neuron for the next postsynaptic neuron. After we're done transmission, a calcium pump will turn on and pump calcium back out of the cell, and our leak channels and sodium potassium pump will reset us to resting membrane potential at the rest of the cell. So that is the most important part: action potential, transmission, summation. We kind of covered the hardest, most nittiest gritty stuff. So that was tissues and tissues. So let's have a quick review of Chapter 1 and Chapter 3. What was important in Chapter 1? We were learning the language of anatomy and homeostatic mechanisms and stuff. So, language of anatomy. This is the frontal region. This is the orbital region. This is the buccal region. This is the otic or auricular region. Okay, let's try that again. This, frontal region. Next, orbital region, nasal region, oral region, buccal region, mental region, cervical region, otic region or auricular region for the ears, cervical region, acromial region, brachial region, antebrachial region, antecubital region, let's see what else. We got mammary region, sternal region, thoracic region. Could also call this the pectoral region. And then we've got, what else do we have up here? See we've got the temporal region over here, occipital on the back, cervical on the back. See what else we can still see on the front. So, abdominal region, umbilicals in the middle. Then we've got our inguinal region, pelvic, pubic. What else do we got? Femoral, patellar, crural. Oh, that's the dorsum of your foot. It's also the metatarsal region, tarsal region. What else do we have here? Carpal region, palmar region, digits. But up here we have the pollex, which is by your palm, and down here we have the hallux, which is by your heel. Okay, I feel like that's most of the things. Oh, the coxal region here, your hip, it's your coxal region, inguinal region right here, groin, pelvic region in here, pubic region down in here. Okay, external genitalia is like pubic. Okay, now what about posterior? Okay, occipital, cervical, scapular. Could call this dorsal back here. Oh, ventral up here, abdominal here. Okay, dorsal there, scapular, vertebral. You could also call this part sacral, lumbar, brachial, olecramal, antebrachial, carpal again, metacarpal now, digits, pollex, femoral. Oh, did I miss the whole top part of that? I did. Oh, shoot. Okay, well, let's just finish this leg. Okay, so femoral. Now back here is popliteal, which rhymes with heel, which rhymes with calcaneal. That's your calcaneus. So calcaneal. Back here is the sural region. On the side is the peroneal region. Popliteal, femoral. That surface is the plantar surface of the foot. So in the anatomical position, that's the plantar surface. What I missed was all up here. Okay, so occipital, cervical, acromial, brachial, olecramal, antebrachial, carpal, metacarpal, digits, pollex. What else can we see back here? So vertebral, scapular. I think those are most of the ones that you guys need to know. Okay, that's chapter 1 for regional terms. For directional terms, anterior toward the front, superior toward the head, inferior toward the feet, anterior toward the front. So you're looking at posterior, here's anterior, lateral away from the midline, medial toward the midline. You're not very bendy. Intermediate is between lateral and medial, intermediate, external, superficial. So my skin is superficial, these bones are deep, the muscles in between are intermediate. Dorsal toward the dorsum, or like posterior for us. It's more like superior for quadrupeds. Ventral is like anterior for us, more like inferior for quadrupeds, means toward the ventral cavity. Anterior, posterior, lateral, medial. What else? We have rostral toward the nose, caudal toward the tail. We have, what else? What else do we have? Lateral, anterior, superior, deep, medial, intermediate, interficial. What else? I don't know. Look at it. Look up in your book. No, I can't say that. Superior toward the head, inferior toward the feet, anterior toward the front, posterior toward the back, lateral toward the side, medial toward the middle, intermediate between deep, deepest, superficial, most external, intermediate between, what else? Proximal and distal. Proximal, closer to the point of attachment, distal, further from the point of attachment. All right. Homeostatic control mechanisms. Okay, homeostasis. Keeping a relatively stable environment despite continuously changing external variables. So, we want to stay in homeostasis. So we've got a set point for everything, where we want to be. We can have a little bit of fluctuation, but we're going to start kicking in negative feedback mechanisms when we get outside that. And then sometimes we want to move further away from that to get to some end point. So homeostasis is staying the same. Negative feedback moves you back. So negative feedback brings you back to homeostasis. So the example that was talked about in your book is body temperature. So let's say it's really hot outside right now and you go for a jog. Your body temperature is going to rise. Your set point is 98.6. My body temperature is 99.1. So there's an average, there's a range, but you're going to get to some higher temperature and you're going to get hot. So that's going to be detected by the sensor, because every feedback loop has a sensor, a control center, and an effector. So the increase in temperature is the change in the variable. That's the stimulus. So that's detected by the receptor. That's going to tell the control center. In the case of heat changes, they're thermoreceptors in your skin, or for the changes in your blood, it's thermoreceptors in your brain. They're going to detect this increase in temperature. So our hot thermoreceptors are going to say that detect that we're hot, send this information along an afferent pathway to the control center. It's going to integrate this information from all of our receptors and decide what to do. Send out an efferent command to the effector. In this case, our sweat glands are going to turn on, our blood vessels are going to dilate. We're going to bring our hot blood to the skin and sweat and lose heat through evaporative cooling. And then hopefully our temperature will drop and we'll come back to normal. Okay, the inverse is also true. Negative feedback will bring us back when we're too cold. Negative feedback always brings you back to homeostasis. So now if we get too cold, let's say I jump in an ice bath right now, then my temperature is going to drop. I'm going to come outside of 98.6. And really, if I'm jumping in an ice bath, probably, I don't know which happens first, but I feel like the thing I would feel first is a massive vasoconstriction. So again, I have a drop in temperature. This is detected by thermoreceptors. These are now our cold thermoreceptors. I'm going to tell my control center, which is my hypothalamus and my brain, it's going to send out an effector, a message to my effectors. And now this time I'm going to vasoconstrict. So I can bring all that warm blood into my periphery, in from my periphery into my vital organs. And then I'm also going to start shivering. So my skeletal muscles now will start contracting, I'll shiver and generate body heat and hopefully come back to homeostasis. So either way, whether I'm too high or too low, if I need to come back to homeostasis, negative feedback is going to bring me there. The other type of homeostatic control mechanism we have is positive feedback. And what happens in positive feedback is we get more of something, more of something, more of something. So we move away from homeostasis. I actually kind of want to use the positive feedback because some people describe the action potential as a positive feedback loop of voltage-gated sodium channels. So let's think about it that way. If positive feedback moves you away from homeostasis, if your homeostasis for a neuron is rest and membrane potential, then what's going to move us away from homeostasis the most is this big depolarizing swing. So this is just helping us bring it all together because you have to know this. I want you to understand the action potential really well. And the depolarizing swing, what's happening with those voltage-gated sodium channels is sometimes described as positive feedback. So what happens is these first voltage-gated sodium channels open and sodium comes in, and that's going to cause more voltage-gated sodium channels to reach threshold. So more sodium is going to come in, which is going to cause more voltage-gated sodium channels to reach threshold. So more sodium is going to come in, which is going to cause more voltage-gated sodium channels to reach threshold. And more and more and more until we get to the end and open up those voltage-gated calcium channels. The other type of positive feedback that we talk about in the body is what happens at the end of gestation or lactation. At the end of gestation, the baby drops. The neural stimulus of pressure on the cervix causes a positive feedback loop to the mom's brain. The hypothalamus is going to release oxytocin, which is going to stimulate the uterus to contract, which is going to cause the baby to push. So that we get more pushing, causes more neural stimulus, causes more oxytocin. So we get more and more and more until the baby's delivered. All right, that's chapter 1. Chapter 3. Just look over organelles. So in neurons, some specialized things that we would find in the plasma membrane are voltage-gated sodium channels, voltage-gated potassium channels in the axon hillock and in the axon. Voltage-gated calcium channels, calcium pumps in the axon terminal. Our chemically gated channels in the plasma membranes in our dendrites and our soma. Okay, well, those are specialized kind of things in the plasma membranes of the cells. We talked about proteins and plasma membranes for chapter 3. The other thing that we talked about in chapter 3 was organelles. We'll see when we get to skeletal muscles, they are highly active. They have a high proportion of mitochondria because they need to be doing a lot of aerobic respiration or making a lot of ATP. They're highly active cells. So kind of review your organelles, make sure you're comfortable with that. New things were cell junctions, so linking plasma membranes together. If we sew them up really tightly, like the hem of your pants, that's a tight junction. We find those in places where you want to control the movement of material between cells, like your blood-brain barrier, your blood-testes barrier. The bladder, where you don't want things leaking out. Desmosome, snap cells together like the buttons on your rain jacket. So there's some control of things, but not a whole lot of control of movement between the cells. Or then we have gap junctions, where those are chemical junctions, where things move instantaneously from one cell to the next. We'll talk more about it next semester, but electrical synapses are using gap junctions. So what we have mostly been talking about is the chemical synapse, where a neurotransmitter crosses the synapse and causes the effect in the postsynaptic cell. But in electrical synapses, you would have a gap junction between the presynaptic and postsynaptic neuron that would result in the generation of an action potential. What else about cells? What else about cells, Kelly? I don't know. I hope we're recording. I'm going to be ticked. Vesicular transport. Neurotransmitters are released by exocytosis, which is when like if you were looking here in a neuron, we would make a neurotransmitter up here and package it into a membrane-bound vesicle to go down through anterograde transport and be stored here. Then when those voltage-gated calcium channels open and move those regulatory proteins, what's happening is we're fusing this membrane-bound vesicle with this membrane and releasing neurotransmitter by exocytosis. Okay, so that's how we get stuff out using a vesicle, how we get stuff in using a vesicle. Let's say this is an infected cell and this is a macrophage. it's going to extend its plasma membrane out and cause these like phagocytic vesicles to wrap around and pinch this guy in. And that would be phagocytosis, bringing in something really large. Pinocytosis is cell sipping, where you bring in little buds of extracellular fluid and the dissolved solutes. Or we can have receptor-mediated endocytosis, where you've got some bound receptor causing responsivity in the cell. We want to down-regulate that. Then we can bring in this whole part of the plasma membrane and bound receptors and stop our signaling. I think those are the most important things from chapter 3. All right, stay tuned for some practice questions. All right, here, let's have some review questions. Okay, the study of tissues is blank. A, cytology. B, histology. C, molecular biology. D, microbiology. E, surface anatomy. And the answer is B, histology. So this was an introduction to anatomy kind of question from chapter 1. So just make sure you review the levels of organization. That will help you know things like that. Okay. The structural and functional unit of all living organisms is A, the nucleus. B, the cell. C, the organ. D, the organelle. Or E, the plasma membrane. The answer is B, the cell. We're going to go to snack and be right back. That rhymes. Did you hear? Which type of tissue forms lining or covering? A, epithelial tissue. B, connective tissue. C, muscle tissue. D, nervous tissue. Yeah, you're right. A, epithelial tissue. The nervous system. A, monitors internal and external stimuli. B, transmits information in the form of action potentials. C, interprets or assesses information. D, maintains homeostasis. E, all of the choices are correct. Yeah, you're right. All of the above. All right. Anatomy is A, the study of function. B, a branch of physiology. C, the study of structure. D, the study of living organisms. E, the study of homeostasis. Alright, yeah, anatomy is the study of structure. Physiology is the study of function. The two work together to help us study living organisms, and all of it, has to have homeostasis. Living organisms surely do. And the physiology and anatomy give rise to that. Alright, the plasma membrane. A, separates the nucleus from the rest of the cell. B, is a rigid protein membrane. C, is not permeable. D, has a single layer of phospholipids. E, regulates movement of materials into and out of the cell. Yeah, you're right. Of these, it's E, regulates movement of materials into and out of the cell. Which type of tissue possesses an abundant extracellular matrix? A, epithelial tissue. B, connective tissue. C, muscle tissue. D, nervous tissue. Yeah, the answer is B, connective tissue. Extracellular matrix has two parts, ground substance and protein fibers. The varying composition and concentration of either or both of those things is what gives each connective tissue its characteristic properties. Cell bodies of the peripheral nervous system are located in A, ganglia. B, Schwann cells. C, the motor division. D, the sensory division. E, nerves. Yeah, the answer is ganglia. Great job. Which of the following describes the position of the nasal region? A, inferior to the mental region. B, superior to the frontal region. C, posterior to the auricular region. D, lateral to the orbital region. E, superior to the oral region. Okay, so this is something that's important to be aware of. Your book calls the auricular region the otic region, but I mentioned, I think, in class the first day, and hopefully in your review, that otic is also auricular. This is where your ears are. So this question was actually written for lay people at first. It said, which of the following describes the position of the nose? Well, the nose is the nasal region, and you have to start learning all of the anatomical terms for this stuff, so I changed it. And it said inferior to the chin, superior to the forehead, posterior to the ear, lateral to the eye, and superior to the mouth. So I changed all of those answers to the correct answers for anatomy. The mental region is the chin, the frontal region is right here, your forehead. The auricular or otic region is your ear, the orbital region is your eye, woo! And the oral region is your mouth. So, yeah, the answer is E, superior to the oral region. The nasal region, your nose, is superior, closer to the head than, okay. Which type of tissue is contractile? A, epithelial tissue. B, connective tissue. C, muscle tissue. D, nervous tissue.
I wanna.
Yeah, C, muscle tissue. Okay, go get it. Rapid removal or destruction of neurotransmitter in the synaptic cleft. A, may affect the ability of the postsynaptic membrane to generate action potentials. B, generates local potentials in the presynaptic terminal. C, is necessary for synaptic transmission. D, may lead to action potentials. E, may stop exocytosis. This time? Yeah, the answer is may affect the ability of postsynaptic membrane to generate an action potential. So if you remove or destroy the neurotransmitter, then if it's an excitatory neurotransmitter, you're definitely going to affect the ability. Okay. All right, those are all my questions. If you have questions, make sure to post them in the Teacher Helping Students Succeed discussion board, and I will see you soon.